Thanks for the introduction. So this is ongoing work. So we're trying to understand trying to model location error using the optimal transport. So far we don't have numerical results. So today basically I just present the some basic ideas and theories in this work, so hopefully this will be a good opportunity for communication. So we would like to hear advices from you guys. We will appreciate it. Thank you. So basically, okay. So first, the problem we look at is the following. So the top is the true model. So you start from the initial state we denote by str, and you suppose it is a true model MTR. Doesn't matter whether we know it. So the true model propagate str to str t plus t, and then suppose we have a projection from the space of the state variable of the true model. We project to the no resolution. Sorry, yes, it's right. So it's project to the low resolution space, and then we run the MLR. MLR is the low resolution model. So we get a forecast. We call it SLR at t plus delta t. So now we compare SLR t plus delta t with STR t plus delta t. So of course there will be a difference. So question is, what is the difference? So basically here I marked it by a question mark. Question is, so what is the difference between the no resolution forecast and the true forecast projected to the low resolution space? So this is the question we have. This is a very general question. Basically, this is a question about model error. So there are many classical ways of handling this, like covariance inflation, additive noise, multiplicative noise, or energy backscattering, or something else that I don't know. So here today our focus is on the location error. Okay. So basically, we ask the following question: does there exist a shift of points on the domain? So basically, the change of coordinates, so that the projection of the true forecast is approximately the no resolution forecast perturbed by this shift of points. Yes. So this is a very the most naive question that we can ask about the location error. But for this question, the answer is very easy to find. So the answer is not always we can find this t. For example, if the projection of the true state is like this, so there is a curve point, turning point like this. But while the low resolution forecast does not have this characteristic, then in this case you cannot find the t, so that the low resolution space, so that the low resolution solution can be transformed to the high resolution state using a transform t. Okay. But here we can still so for this question the proper tool is the optimal transport. So basically this is a theorem in the theory of optimal transport. So this says the following: so given two smooth probability density functions f and g, then there exists a map T defined on the points where g is non-zero. Okay, so that f of t, f composed with t times the determinant of the Jacobian of t, equals g of x at all the points where t is defined. So this is the second argument is that t can be found based on the loss function. So you by minimizing loss functions. So what does this mean? So here I find a figure about the optimal transport. So suppose your original distribution is a blue curve, and so f is a blue curve, and then g is a red curve on the most right hand side. So basically, this optimal transport says that you can gradually transform this blue distribution to the red distribution. Okay. So in other words, so basically, if you forget that the f and g must be probability density functions, so suppose your f is some state variable and g is a state variable, then basically, or roughly speaking, this means that there exists a transport T such that this state variable G, the distribution of the state variable G, not distribution, I mean the field of G, is equal to F composed with T times the Jacobian T. Okay, so this is a optimal transport theorem that we will use. So there are still some mathematical questions here. So that T is only defined on the points where G is positive. So the zeros of G. So if G, because here G is a positive probability distribution function, so G may have zeros. But this G may be, so this 0 points may be tricky to handle. So this T, what is the performance of T? What is the behavior of T at these 0 points? Still, we still need to figure it out. So the second point is the most important one. So basically, so in the optimal transport theorem, we require that f and g to be energy, to be positive, to be probability density functions. So this means that we can apply optimal transport to the energy profiles of the physical state, like kinetic energy, temperature, or mass, etc. So this is nice because because energy profiles are always non-negative. So you can think of energy profiles as the probability density functions. If the state variable is positive and negative, for example, it's a velocity. So if it's the first component of the velocity field, then I don't know if we can apply optimal transport directly to that variable. So okay, so we're still studying this one. Okay. So now let's take an example. So now let's consider the surface residual strophic model. So basically, the original model is like equation 3 and equation 4. So buoyancy, the state variable buoyancy, is propagated by this Jacobian of B and C. And C is not another state variable. C can be directly computed from the buoyancy in equation 4. Okay.
Oui, salut. Salut, tu m'entends?
And so in the case of SQG model, so we can consider we can look for transport T and constant A, which is positive, so that the projection of the true buoyancy squared equals constant A times the low resolution buoyancy squared composed with T times the determinant. So basically, this means that we can find the transport T such that the low resolution state can be associated with the true state. It remains a question, what is a T? But here, what we want to show is that there exists such a T, so that the true state is exactly equal to the can be exactly associated with the low resolution state in this way. Okay. So now if we define B theta, so basically we define B theta to be the square root of A times the B low resolution buoyancy composed with T times the square root of the determinant of Jacobi. So if we define B theta in this way, so basically this means that B theta should have the same contour as the projection of the high resolution buoyancy. Okay. So this is nice because our goal of fixing the low resolution state is to change it so that it has the same contour as the high resolution state or true state. Yes, but still, again, so here what I'm representing here is that there exists such a transport T such that B theta have the same contour as the high resolution state, but we do not know what t is. So if we want to use this thing, if we want to apply this idea to the to our model, so basically we need to model the transport t. We need to have a model for the transport t. So basically here we need to build a model for t. So this is the model for t will give you a modeling, will give you a model of the location error. And besides this, we still need to answer the following questions. So is t continuous or differentiable on the points where g vanishes? So this is a question for the optimal transport theory. And secondly, how do we construct the optimal transport from snapshots of TR of true state and no resolution state? There are some code online. So, but here again, the tricky issue is that what if the energy, or what if your snapshots have some error points? What if your ELR or ETR vanishes at some point in the domain? So maybe this has already been solved, but it's still a question for me. So I'm still trying to understand whether this whether there is a reliable method for constructing T for arbitrary arbitrary probability density functions. But now, if we want to, if we ignore these two questions, if we just want to use optimal transport theory to model the location error, so basically, what is the most important emergency is to model the optimal transport T. Okay. So basically, we model T using a stochastic process. So T of X. So we perturb the point X with a Brownian motion. Okay. And then we fix. We change low resolution forecast in this way in equation 8. So basically we compose the low resolution state with this perturbation of points times the square root of R quantity. This R quantity basically is a volume expansion rate. So it's computed like this, and it corresponds to the Jacobian of the transport T in the optimal transport theory. Okay. So now we present what we want to do. Okay. So basically, if the original SQG is like this, this is the original SQG equation, which is equation 11. And after we modified, the SQG will be like this. So basically, you will be the original equation plus this thing. Okay. And because the SQG conserves energy, conserves the b squared, integral of b squared. And because here we, and according to optimal transport theory, after you do this modification, b squared is also conserved. Okay. So maybe this one, this is a one-dimensional example. So maybe it's easier to read. So if the original PD is like this, then the eventual PD will arrive is the following, is in equation 18. Okay. But it's still, there are still some issues here because basically it's because due to the conservation of quantity. SQG does not only conserve b squared, it also conserves the integral of b. So therefore, after we do the modification, we also need to conserve this quantity. So, but we cannot get to this conservation more directly. So we need to add more constraints to the basis function of your Brownian motion, and to the variance of your Brownian motion. So basically, we need these two more quantities. So this means that this EI, the basis function, may be adaptive. Maybe it's not. It should not be fixed in time. Okay. So summary. So what did we do? Okay. So we designed a scheme to model the location error of low resolution forecast. So basically, what we want to do is we want to build this model so that when we do forecast, we do forecast using ensemble or particle filters, using ensemble forecast or then we have a better representation of the uncertainty. So this is what we want to do. Okay. And here we consider the uncertainty to be the location uncertainty. Okay. So therefore we use the optimal transport to represent the location error. And so we change the original equation. So here basically we add some noise term to the original equation, and we also add some deterministic term to the original equation. Okay, so basically all of these are aimed at have a better representation of the uncertainty in the forecast. Okay, so but there's still some questions that we haven't answered. So what is the behavior of t at the points where g is 0, and how to construct the t derivative from snapshots? And another point is that if you want to conserve s squared, you change SLR in this way. And if you want to conserve s itself, you change SLR in this way. Okay, you don't throw away the square root for r. But if you want to conserve both of them, you need to have more constraints on the basis function and gamma I, and the variance of the Brownian motion. So the future work, I think this is a very this work has a very large potential, because we are yes. So basically, this tells us we can look at the location error in a different way. So for the future work, we basically first we need to solve the mathematical problems. And then for the numerical implementation, we will try it on the SQG model. And also, this is nice. This is a nice because we can also apply this theorem. We can also apply this optimal transport theorem to the real data, because in the real data, in the real applications, in the real world, we have the real analysis time series. So we can use this real analysis time series and the low regression model to find the location error of your location of your low regression model. Okay. And another thing which I think is very interesting that we are doing now is that we want to design a data simulation scheme that handles the location error explicitly. Yes. So basically, this will also involve something about optimal transport. So yeah. So this is my presentation. Okay. So maybe the rest time can be used for our questions. Okay. Thank you.
Thank you very much. Are there any questions or comments, discussions?
Maybe I can start.
Yeah.
Thank you, Yikun. Very interesting. I just wanted to clarify something. Because here, for instance, in your SQG model, I don't really see the dimension of your T transformation. Is it a 1D or 2D 2D PDF?
T is a map from a domain to a domain.
And yeah.
T is a map from domain to domain. Okay, so in here, so okay, yeah, here. Okay, so in SQG, basically it's a two-dimensional domain. SQG is an equation for a two-dimensional domain, so it can be a bounded domain or a torus. Then the T, this map T is supposed to be a map from the domain to a domain itself. Yeah.
Okay. Okay.
Yes. Yeah.
And I have another question. It's about R. Can you go back to the definition of R in the optimal?
In here?
Yes.
Slide?
Yeah. Can you explain it again, please?
Yeah. So you see in the optimal transport theory, okay, let me look at this. So in equation 5, okay, so basically we say that we can find the transport T so that ELR squared should compose with T times the determinant of Jacobian of T is equal to the destination function. So BT, the projection of BTR is our destination function. Okay. So basically in here, in equation 8, we say we construct S tilde to be SLR composed with T times the square root of RTX. So the first term is easy to understand. SLR composed with T is just BLR squared composed with T. Okay. But what is the determinant of Jacobian of T? So it is the square root of R. So basically, because here T is we model T as we model T using a stochastic process, so we can compute T1 which T2 which dTn. Okay. So basically, there is an expansion of a volume element. Okay, when you transform, we have a map. The map will either expand the volume or shrink the volume. So basically, this R is a expansion rate of the volume for this specific model of T.
Yeah.
Similarly, equivalently, this determinant of Jacobian is also the expansion rate or shrink rate of the volume for the map T.
Okay.
Yeah.
I see. And just a last question, maybe comments, but you say in your last point that there is you want to implement that in data simulation, and
yes.
This transformation to go from the basically to go from low resolution to high resolution make it I think it's somehow very similar to sorry, how can I say that? You say in data simulation when there is in the observation equation, when you have observation equal h x, and sometimes the observation is high resolution and the state of the system is low resolution, and there is a problem of what is the word for that? Sorry.
Interpolation error?
No, it's representativity error. Sorry. Yes.
Okay.
And I think there is maybe a link between the representativity error and this transformation. Do you have the same feeling?
Yeah, for the point 4, so basically we are thinking about the following. So now suppose you're suppose you are running an sample forecast. You want to forecast a hurricane. Okay. So basically you start from the same initial condition. And one member says that this hurricane will go here, and another member says hurricane will go here. So now how do you find the mean of these two states? How do you find the mean of these two sample members? If you just use arithmetic mean, or I don't know, if you just sum these two states and divide it by 2, then it will give you something very strange. We have 2 IOs, but so here we need to consider how to compute the mean here. So basically, this is when you compute the mean of these two states, you need to consider basically it's a mean of the location. Okay. So basically, right. So for example, for another example, if you have if your state variables, if you have 2 samples of a state variable, both of them are Gaussian shape. One is here and one is here. Okay. So now what will be the mean state of these 2 samples? Intuitively, it should be Gaussian in the middle of them, right?
Yeah.
So basically, in the theory of optimal transport, basically this optimal transport also give you give you a distance called a vector state distance. So basically, if we use the optimal transport theory, basically you want to find a Gaussian state so that the vector state distance between this Gaussian state and these two samples, the sum of these two distances are minimal. So basically, this will tell you the state to be the Gaussian in the middle of them. So this is a better definition of the mean for the location error. So this is what I mean. So this is just starting point. Yeah. So, but for the data simulation scheme, we can also have corresponding modifications. Like,
but, I see now. Yes. Okay.
I think this is interesting because it does not work on the. So because it handles location error explicitly, so I think it's nice. Yeah.
Okay, so there is a simple question from Simon in a chat message.
Okay. So I didn't see it.
They have already published, or is it ongoing work?
Ongoing work.
No publication yet.
There is a. I saw one publication about this. So basically, they model location error in this way. Yeah, but it's not a perfect. I don't think it's perfect solutions because this is too empirical. In this case, you have to. This T does not exist. Okay. So, yeah. So for this idea, there is a publication work in February of this year.
Okay.
Yeah.
Okay. Yeah. Are there any other questions or comments, discussions? So you mentioned about the low resolution model and high resolution, both true system.
So, yeah, in OC, this can be a high resolution model, but in the real world, it can be a reanalysis or. Yeah.
Oh, the true system. So you have a true system and some low resolution representation of the true system in this problem. But if we just focus on the location error, we have many other potential applications, for example, like precipitation data assimilation that we have been working on for a long time so far. We tried to assimilate image data. Precipitation usually have location error. So measure the location error is not simple. So we developed some methods to measure the location error, but this can provide another measure to the location error.
Yes, so basically, I think you are talking about that there are already some methods that in the data simulation that handle this location error. But here, what we do in this work, what we present is that we want to have when we do ensemble forecast, we want our ensemble spread to have a better representation of the location error. So basically, here we do not have additive noise here. We don't just have additive noise, but we have a perturbation of the location. So yeah, so basically this is for the this is like a covariance. This is a covariance inflation method. You can think like that. It's not a. This modeling of location error is a covariance inflation method. So it's like how you perturb the ensemble forecast at every time step, so that the covariance inflated. And then for data simulation part, you are right. There are already some method to fix the location error. Yeah, that is for data simulation. And yeah.
Yeah, well, I meant I didn't mean that there is a good existing method or something. I was curious if we could use.
But you're right. I would say some method.
We could apply this method for like the similarity index of.
Yes. For example, in particle filter, we do resampling. Right? When you do resampling, so you can consider it to perturb the location of each particle by some t. Okay, you can generate some random t using this stochastic model, equation 7. You can generate random t, and then you perturb you compute SLR composed with T times square root of R. So basically, this will give you a perturbation of your location of your current state. Yeah, so this, but I don't know if it's useful. Just some simple idea.
Yeah, I think that we have many data like from camera, the optical sensor, or some radiation sensors can capture the image of some object. Like we are also working on data simulation of Venus atmosphere, and we have like optical camera or infrared camera, and we have an infrared image of the full disk or the part of the Venus atmosphere, and we have a model that have a lot of errors. We don't have a good model. So in your first slide, you showed there is a true process, and we have the camera image of the true process, let's say. And we have some bad model that's a low resolution representation of the bad model of the Venus atmosphere. And maybe this framework can work for that kind of situation.
Yeah, so basically here, because this is based on basically the core theory here is the optimal transport, and optimal transport can be applied to the snapshots. Therefore, when you have real data or when you have observation data, you can directly apply it, and then you can learn what is the location error at every time step. So this is the nice part. Yeah.
Yeah. Thank you very much. Are there any other comments, questions?
Just a comment. I think this tool, what you are presenting, RIKEN, it can be a diagnostic tool to a kind of new metric to evaluate, for instance, the quality of models compared to observation. So this is exactly, I think, related to what Takemasa says. So this can be very interesting operationally to validate, I don't know, forecast.
Yeah,
thank you.
Maybe.
Yeah,
So,
and that's what we.
I'm still thinking about the mathematical questions. So
yeah, that's what we need for data simulation, actually. So, yeah, if you think about the particle filter, then it's much simpler. If you have a similarity index, you can calculate the weights to each particle based on the similarity. So if this can work as a similarity index, then yes, we can evaluate the model performance, but we can also use that for data simulation.
Yes, right.
Yeah, very nice. Are there any questions or comments? If not, we would like to move on to the second talk. Thank you very much.